Hello everyone, this is Vrishali and you are watching Digital Signal Processing series. So in previous two videos we have studied in the first unit, that is DSP preliminaries, sampling theorem, aliasing effect and so on. And in second video we have studied DFT, that is a discrete Fourier transform, DFT, FFT, its properties and all. So in this third unit, in third video, today we are going to discuss Z transform. So the contents that we are going to discuss are as follows: the need of Z transform, then what is the relation of a Laplace transform as well as Fourier transform with this Z transform, then properties of ROC. So what is ROC? Region of convergence. What is that? That also we will discuss, and the properties of Z transform. Then we will see what is the relation of pole locations and time domain behavior. Also, we will see the causality stability consideration for LTI systems. Then, with Z transform, we will study inverse Z transform as well with the help of two methods. One is power series method, which can also be known as the long division method, and the second one is partial fraction expansion method. So let us start with the first topic, that is need of Z transform. So Fourier transform provides valuable techniques for frequency domain analysis and the design of CT signal and LTI system, while the Z transform provides a valuable technique for analysis as well as designing of DT signal and DT LTI systems. Z transform has a real and imaginary parts like Fourier transform. A plot of imaginary versus real part is called as a Z-plane or complex Z-plane. The poles and zeros of DT system are plotted in this Z-plane. The pole zero plot is the main characteristics of DT LTI systems. The stability of this system can be checked using pole zero plot. Entire family of digital filters can be obtained from one prototype design using this Z transform. The solution of a differential equation can be simplified using Z transform. So these are some advantages, or you can say there is a need why this Z transform is coming into picture. So let us start with the basic thing, that is the definition of Z transform. So Z transform of discrete time, that is a DT signal x of n, is defined as, it will be given with this expression, that is x of z is equal to summation n runs from minus infinity to infinity x of n z raised to minus n. So this is a basic definition of Z transform, where z is a complex variable, that means it will have a real as well as imaginary part. In polar form, z can be expressed as z is equal to r e raised to j omega, where r is the radius of a circle. So, one-sided zt, that is a one-sided Z transform, can be given as, how to consider it as a one-sided or double-sided? So, there is a criteria that if the summation runs from minus infinity to infinity, that means this is a bilateral or double-sided Z transform. If the summation runs from 0 to infinity, that means only at one side of axis, only positive side of axis. So that is called as unilateral or single-sided Z transform. Now, in the above equation, if you observe that summation runs from minus infinity to infinity, that means it is a bilateral or double-sided Z transform. Now, to give expression for a one-sided Z transform, can you guess that what will be the limits for the summation? Yes, it will be 0 to infinity. So, this is a one-sided Z transform, that is x of z. Summation runs from n is equal to 0 to plus infinity x of n z raised to minus n. What does that mean? This n will have only positive values. It will not go on the other axis. This relation can be further written as x of z is equal to z of x of n. So this is a short version, or you can say another version of writing a Z transform. That is, x of z output can be given as z of, that means Z transform of this x of n dt signal. Now depending on the application, if your input signal x of n is double-sided, then obviously you will use double-sided Z transform. If x of n is a single-sided, then you will use unilateral or single-sided Z transform. Now let us understand the relation between Laplace transform and Z transform. So Z transform is a general concept for transformation of discrete time series, whereas Laplace transform is a general concept for transformation of continuous time processes. So this is a basic difference in Laplace transform and Z transform. So Laplace transform of the continuous time signal x of t can be written as x of s is equal to integration 0 to infinity x of t e raised to minus st dt. To obtain the dt signal x of n, you have to sample the x of t with sampling time t. Now, here you can see that as the Laplace transform is taken for the continuous signal CT signal, so as x of t is a continuous signal, you are taking integration of that CT signal. X of t is continuous signal, x of n will be dt, that is a discrete signal. Okay, so whenever x of t is there, you have to integrate it as it is a continuous time signal. Whenever the x of n will be there, dt signal, that time you will take a summation as it is a discrete in nature. Now, if you want to convert this x of t, that is your continuous signal into discrete signal, what will you do? Sampling. So sample this x of t with respect to sampling time t. Now, instead of writing x of n, you can also say that x conjugate t. So both will have a same meaning. So this x of n or x star of t can be given as, or x conjugate can be given as summation n runs from 0 to infinity x nt delta t minus nt. Now Laplace transform of this signal can be given as x conjugate of s summation n runs from 0 to infinity x nt e raised to minus nts. Now you can see on the right hand side x of n is there, that is a dt signal, that's why we have taken summation. If it is a CT signal, you have to take integration. Now t is replaced by nt and x conjugate is a dt signal. Thus summation is used instead of this integration. Now putting z is equal to e raised to st in above equation, instead of e raised to st, we are going to substitute z. How it will look like? X and t will remain as it is, z raised to minus n, because you are going to replace this e raised to ts by z. So this is nothing but the z transform of x and t, right? So how you can compare that? Z transform of x conjugate t will be equal to x of z, which is given by this above expression. What does that means? The relation between Laplace transform and Z transform can be given as z is equal to e raised to st. What does that means? If you substitute z is equal to e raised to st in the Z transform, it will exactly look like Laplace transform. Or if you substitute e raised to st as a z in Laplace transform, then it will become a Z transform. So z is equal to e raised to st is the relation between Laplace transform and Z transform. Now similarly, let us understand what is the relation between Fourier transform and Z transform. So Fourier transform of dt signal can be given as x of omega is equal to summation n runs from minus infinity to infinity x of n e to the power minus j omega n. Now z transform of the above sequence x of n is given as x of z is equal to n runs from minus infinity to infinity x of n z raised to minus n. In polar form, you know that z can be expressed as z is equal to r e to the power j omega. Now if I want to get relation between Z transform and Fourier transform, obviously I should write both the equation in common form. So that's why I'm going to substitute Z is equal to R e raised to j omega in the polar form. So how it will look? So in this, R is nothing but the radius of a circle and Z is a complex variable. So obviously R will be magnitude of Z, whereas omega will be the angle of Z. Now Z transform of the sequence is given by this formula, and in polar form, if you substitute this Z is equal to R e to the power j omega in above equation, it will look like this. Now multiply the n minus n power inside. It will look like r raised to minus n e to the power minus j omega n. What I will do, if I look it as a Fourier transform, then you can see that the Fourier transform is given as x of n into e to the power minus j omega n, right? What does that mean? This is the inside bracket term is your x of n. This is nothing but this is a z transform of x of n r raised to minus n. So evaluating this equation on a unit circle, r will become 1. So whenever the value of r is equal to 1, that time you are getting the Fourier transform of this sequence. Thus, the Fourier transform and Z transform are evaluated on a unit circle. So whenever the r is having a value is equal to 1, that time Z transform of x of n will be equal to Fourier transform of x of n. So this is a relation between Fourier transform and Z transform. Now this is one of the example that if x of n is equal to unit sequence, then how to calculate a Z transform? Just substitute n is equal to 0, 1, 2, 3 as, and by this series 1 plus r square, which will be given as 1 upon 1 minus r, where r is less than 1. So similarly you can write the equation for x of z, that will be z upon z minus 1. So the region of conversion will be the values of z for which it will converges. So z raised to minus 1 will be less than 1. So mod of z will be greater than 1. Similarly, this is the another example that if the sequence is a raised to n u of n, then how to calculate the z transform? Again, you have to just go on substituting the values of n is equal to 0, 1, 2 similarly, and you will get the final expression. In this case also, the region of convergence is mod of z is greater than a. Now what is the ROC? What is this region of convergence? So Z transform is infinite power series, but it exists only for those values for which Z in the series converges. All the values of Z for which series x of z converges, which gives the finite values, are known as region of convergence. The ROC of x of z is nothing but the set of all values of z for which this x of z has a finite value. Condition that must be satisfied for the convergence is nothing but summation n runs from 0 to infinity, x of n z raised to minus n should be less than infinity. Now what are the properties of ROC? So ROC is the ring or a disk in z plane centered at origin. ROC cannot contain any poles. If x of n is a causal sequence, ROC is the entire z plane except z is equal to 0. If it is a non-causal sequence, ROC's entire z plane except at z is equal to infinity. In case of finite duration sequence, two-sided sequence of ROC is entire z plane except z is equal to 0 and z is equal to infinity. Whereas if it is an infinite duration sequence, then it will consist of ring in z plane bounded on interior or exterior by pole and not containing any poles. ROC of LTI stable system contains unit circle. ROC must be connected in region. Now, let us understand the Z transform and ROC. Two cases are there, finite sequence and infinite sequence. So, we will see in detail for the finite sequence. So, it can be classified in three types: right-handed sequence, left-hand sequence or two-sided sequence. In right-hand sequence, n will be less than n0, which can be positive or negative, but it will be finite, and its ROC will lie in entire z plane except at z is equal to 0. In left-hand sequence, n is greater than or equal to n0. It can be positive or negative but finite, and ROC will be entire z plane except z is equal to infinity. And in case of two-sided sequence, it is a finite duration at both left and right hand, and ROC will be entire z plane except at z is equal to 0 and z is equal to infinity. Now let us understand that with help of example. So the first sequence is causal signal, that is a right hand sequence. The second sequence is anti-causal and the third one is non-causal. So here you can see this is a causal sequence, that means 0 place stand over here, so it will have all the positive values. In anti-causal left-handed sequence, that means 0th place stands over here, so all will have a negative values. And this is a two-sided sequence, that means here the 0 is placed, it may have a positive as well as negative values. So how to calculate the Z transform of this? I will tell you with the help of one example. Let us consider the first case. So in this case, x of z can be given as, what you have to do, just go on substituting the n value as 0, 1, 2, 3 and substitute the values of x of 0, x of 1, x of 2, x of 3 here. So you will get the final x of z, Z transform of this sequence. So similarly, you have to substitute the values of n according to the signal. Now these are some common Z transform pairs that you may need in solving the examples. Then what are the properties of Z transform? So similarly, DFT, Z transform also contains the property of linearity, then the shifting theorem and convolution. So if you observe, the properties are same, that x of 1 and x of 2 here are the sampled sequence and a or b are arbitrary constants. So linearity property, that is the Z transform of ax1 of n plus bx2 of n will be equal to a Z transform of x1 of n plus b Z transform of x2 of n. Similarly, the shifting theorem, that is Z transform of x n minus m will be obviously z raised to minus s m x of z, and the convolution property, that is the x of z will be given as x1 of z into x2 of z, where x1 of n and x2 of n are convoluted with each other in time domain. Now, what is the pole zero plot? So, use of Z transform to plot the pole zero of system is to check the stability of system and to obtain the impulse response. Then the pole zero plot can be given as x of n, h of n and If you convolute x of n into h of n, you will get y of n. So similarly, in Z transform, multiplying x of z by h of z, you will get y of z. We are going to denote zeros by this symbol and poles by this symbol. The ROC, that is the region of conversion, will be shaded in the grey color. Now this is a transfer function for pole 0 of a system. So in numerator, if you say h of z can be given as bk z raised to minus k, and in denominator 1 plus ak z raised to minus k. Now zeros of this will have values of z for which h of z is equal to 0. And how to calculate poles? The values of z where h of z is infinity. Now if the numerator is 0, that means h of s is 0. So if numerator is 0, you will get zeros of the system. If denominator is 0, that means h of z is equal to infinity. You will get poles of the system. So above equation contains both poles as well as zeros. So that's why this is called as pole 0 systems, where n poles will be there and m zeros will be there. When x of z is a rational function, the ratio of polynomials in z, roots of numerator polynomial are referred as the zeros, whereas the roots of denominator are referred as the poles. No poles of x of z can occur within the region of convergence, since the z transform does not converges at poles. Now what is the relation between pole location and time domain? We will see that with the help of different examples. So let us consider one by one all the examples. So x of n is, suppose, decaying exponential signal as shown in this figure. Okay, so how to write that? A raised to n u of n, but your limits will be alpha running from 0 to 1. Now to obtain the zeros, equate the numerator is equal to 0. Now you know that the z transform of this sequence can be given as z upon z minus alpha. Equate numerator is equal to 0, so z is equal to 0. And to obtain poles, equate denominator is equal to 0, so z minus alpha is equal to 0. That means z is equal to alpha. So x of z has zeros at z is equal to 0 and pole at z is equal to alpha. That means ROC is a exterior to the circle of a radius alpha. So this hashed region is nothing but the ROC for this. Let us understand another example where alpha is equal to 1. That means x of n is a constant signal. Now in this case, to obtain zeros, again equate numerator, z is equal to 0, equate denominator. Now in this case, alpha is equal to 1. So that's why z minus 1 will be equal to 0. That means z is equal to plus 1. So x of z has zeros at z is equal to 0. Poles at z is equal to 1. That means a unit circle. So this will be the region of conversion. In third case, alpha is greater than 1. Now this is a rising exponential signal. Again, by equating numerator and denominator to 0, what you will get? 0 at z is equal to 0 and pole at z is equal to alpha. So this is a ROC. Fourth case, alpha lies between minus 1 to 0. So alpha will be less than 0, that is the negative number. That's why your sequence will become minus a raised to n u of n. So for all even values of n, it will be positive. Hence you will get 0 at z is equal to 0 and poles at z is equal to minus alpha. So this is the region of conversion. If alpha is minus 1, then again it is a negative number. So a raised to u of n will become minus. Now signal oscillates between -1 plus 1 as alpha is equal to -1. So in this case 0 will be at z is equal to 0 and pole will be at z is equal to -1. So this will be your region of convergence. And at alpha less than -1, again by following the same procedure, this will be the region of conversion. So by considering these different examples, we can understand the relation between pole locations in time domain behavior. Now let us move towards the next topic, that is the causality and stability consideration for LTI system. Now you know that x of z is equal to z upon z minus alpha for causal signal. So causal system can be represented as h of n is equal to 0 where n is having the negative values, that is the h of n is right-handed. Hence pole will be at z is equal to alpha by equating the denominator is equal to 0. So ROC is mod of z greater than position of pole. If there are multiple poles, then ROC will be mod of z greater than maximum of poles. Also, the system is stable if the impulse response is absolutely summable. Now, integration n runs from -infinity to infinity, mod of h of n is less than 0. So the transfer function of a discrete time signal is given by the z transform h of z is equal to summation h of n z raised to minus n. Now taking the mod on the both sides, it will look like this. As absolute value of sum is less than sum of absolute value, so evaluate this z transform on the unit circle. H of z will be less than the mod of individuals. So this system is stable only if h of n is less than infinity. That means negative values. A system is stable if unit circle is a part of ROC. That means a unit circle must be present inside the ROC. So what is the condition of causality? ROC is mod of z greater than maximum of poles which is exterior to circle of a radius of maximum pole value. And what will be the condition of stability? ROC should contain a unit circle. So both conditions of causality as well as stability will be satisfied only if all poles of the system lie inside the unit circle. So these are the two conditions to determine whether the system is causal or stable. So considering P1, P2, P3 is less than 1, that is the unit circle is a part of ROC, that means as all poles are lying inside the unit circle, so the system is stable. Now in this case P3 is lying outside the unit circle, so that's why this system is unstable. So this is a condition how to check the system causality as well as stability. And the last part, that is the inverse Z transform. So these are the two representation of Z transform. H of n can be given as Z transform will be H of Z. If you take inverse of it, it will be again H of n. Or you can write in terms of x also, it is one and same. So this inverse Z transform can be obtained by two methods. The first one is power series or a long division method. The second one is partial fraction method. Let us see the examples of both. So inverse Z transform, expand the x of z into a power series of the form like x of z is equal to x of n z raised to minus n. Note that if x of n, that is your input signal, is causal, then ROC is exterior to circle and the values of z can be negative powers. If x of n, that is the input signal, is anti-causal, then ROC will be interior to circle and values of z will be positive powers. Now let us understand this power series method with the help of one example. Now x of z can be given as 1 upon 1 minus 1.5 z raised to minus 1 plus 0.5 z raised to minus 2. Now how to calculate z transform? From this you have to take an inverse z transform. So for that we are going to use power series or long division method. So perform the normal division method. Now here you have to write the numerator, that is 1, and this will be your denominator. Now by considering the first term, you have to write the terms in descending order. So by considering the first term, that is 0.5 z raised to minus 2. How to get 1 from this term? You have to multiply it by 2z square. So if you multiply 0.5 z raised to minus 2 by 2z square, you will get 1. So the first revision will be 2z raised to 2. Now multiply this 2z raised to 2 by entire equation, you will get this. Subtracting from this 1 minus 1 0, minus of minus 3z will become 3z minus 2z square. Again, how will you get 3z from 0.5 z raised to minus 2? Multiply 0.5 z raised to minus 2 by 6 z raised to 3. You will get 3z. So what you have to do, like normal division method, just keep on eliminating first term by multiplying it with first term of your denominator. So in this way, if you go on doing this, you will get some expression. Do till 3-4 steps. So this will be your final answer. So x of z can be given as 1 plus 1.5 z raised to minus 1 plus 1.75 z raised to minus 2. So how to get x of n from this? Just take the coefficients, that is the constant terms, and that will be your x of n. So this is a power series method or long division method which is performed using a normal division process. Now the second one is partial fraction method. So h of z can also has a different form than all the listed pairs in the z transform table. Thus h of z needs to be rearranged to become like one of the forms listed in that table. So this can be done by performing the partial fraction expansion using this formula. What you have to do? Make a form of your numerator in terms of bk z raised to minus k and make a form of denominator in the form of ak z raised to minus k. Let us understand how to do that with the help of one example. So suppose this is your x of z, that is 1 plus 3z raised to minus 1 upon 1 plus 3z raised to minus 1 plus 2z raised to minus 2, where region of convergence is mod of z greater than 2. Now eliminating the negative powers of z by multiplying and dividing it by z raised to 2. Now identify what is the highest power of z in this total expression, that is 2. So you have to multiply it by z raised to 2 so that this negative power will eliminate. So multiplying denominator and numerator by z square, you will get this final expression. Now take z common from numerator. So z into z plus 3 will be your numerator and denominator will be z square plus 3z plus 2. So this can be written as, this is nothing but the multiplication of z plus 1 into z plus 2. So your numerator will be z plus 3 upon denominator will be z plus 1 into z plus 2. Now this z which was in numerator to this which was with multiplication, it will go on the left hand side of is equal to sign and it will go in denominator. So x x of z by z will be equal to z plus 3 upon z plus 1 into z plus 2. Now, above equation can be written in the partial fraction form as x of z upon z is equal to a upon z plus 1 plus b upon z plus 2. This is a normal conventional partial fraction method that you have studied in lower semesters. Now, how to calculate this a? Just substitute. See, if you want to take a, then what will you do? This z plus 1 will go into this side. So z plus 1 into x of z upon z, where z is equal to minus 1. If you go on solving, you will get a is equal to 2. Similarly, you can get the value of b. So once you have got the values of a and b, substitute it over here. It will look like this. So this z, which was in denominator, will go in numerator on the other side of is equal to. So that's why the x of z will be 2z upon z plus 1 minus z upon z plus 2. Since the ROC is z greater than 2, so this sequence is causal. So x of n can be written as 2. Now z, here the sequence will be minus 1 raised to n u of n minus 2 raised to n u of n. So minus 1 raised to n u of n will give you z upon z plus 1. So this form, right? So that's why this will be a sequence. And how to get that? By using inverse z transform. That means you have calculated x of n from this x of z. So this is the another method for inverse z transform. So thank you. Stay home, stay safe, and happy e-learning.